Welcome to another GraphGeeks talk. I'm Amy Hadler, and I'm delighted to introduce our speaker today, which is Max DeMarzi. He's going to guide us through some tips and tricks for better graph data modeling. Max brings over a decade of graph experience, 8 years with Neo4j, followed by his work with Amazon Neptune, currently with relational AI. I'd also say he's a very passionate educator. So he actively blogs, contributes to open source projects, and in my opinion, always looking for, I would say, a more elegant graph solution to complex graph problems, which is always fun. So thank you for joining us today, Max, and go ahead and take it away.
So today we're talking about graph modeling mastery and how to optimize your graph database models for better performance. So once again, my name is Max DeMarzi. You can find me at Max DeMarzi on Twitter or whatever it's called nowadays, or maxdemarzi.com, or on GitHub. You can email me if you wish. Amy already said the places I worked at. I also worked on my own little graph database called RageDB, just a way to have some therapy writing thousands of lines of C++ code. But today we're going to be talking about modeling and graph modeling, not mail modeling. And before I start my presentations, I always like to jump in and do an annual state of the market check. So this is the dbengines.com graph databases ranking for the different types of databases, if you will. And back in 2023, we were at 1.8%. Today, we're at 1.5%. So we're down a little bit from 2 years ago. If you look at the trend line, you see things started to tick up around 2015 or so. And then around 2022, we got this downward trajectory as we are headed toward oblivion and obscurity. So you might think, well, it looks like graph databases just don't have much of a future at all. And you would be right, but wait, there's a small, tiny little upward shift happening right there at the end of this year. And that is a little ray of hope. You might even say it's an AI of hope, and let's just hope it's not a hallucination. All right, where was I? Oh, yes, I was talking about graph databases. And the thing that makes graph databases special is that they have relationship chains. These chains allow each node to know who the neighbors are right away. They don't have to search for them. If you're looking for your neighbors in different types of databases, typically involves searching, looking in an index and trying to find where they might be. In graph databases, you know exactly where they are. So if you needed to borrow, for example, a cordless power drill from one of your neighbors, how would you do that, right? You would knock on every door and say, hey, neighbor, do you happen to have a cordless power drill I could borrow? You're going to say no, then you go to the next neighbor, and you say no, you go to the next neighbor, and so on, until you get a yes. But what if you already knew which neighbors owned a cordless power drill that you might borrow, right? What if all the neighbors that owned cordless power drills had red doors for some magical reason? And you could just go to that red door and knock on that one and not waste your time asking the neighbors that wouldn't be able to help you. Okay? That is what I consider the secret to graph databases. And that's the trick to understanding performance of graph databases and then everything really else that makes a difference of why you want to use a graph databases versus other databases. And it's partitions. Every node has its relationships chains partitioned by type and by direction. Right? Now, keep in mind, this is if you model your database correctly. If you make a mess of your model, then you're going to lose this magical property of partitioning. So let's talk about what that means. Let's start with the basics of graph modeling. So we need to first follow some rules and establish some guidelines. The rules are going to be really simple. Most databases will adhere to these general rules. So relationships are only between two nodes. You can't have a three-way. You have no dangling relationships. So there's no one-way relationships. Everything is connected both ways. Now, there's a little star next to it. We'll get to it. Relationships must have a type. They can't just be these two things are related. They have some kind of semantic meaning behind their relationship. They could be friends. They could be neighbors. They could be family members, whatever. There's some kind of relationship attached to it. They have to have a direction. Now, you don't have to treat the nodes or the relationships as if they had a direction. You can ignore the direction, but usually they have a direction. You typically can't change the type of relationship. Once you have it, you're stuck with it. If you want to change it, you really have to delete the relationship and create another one. And they're unlimited. A node can have 0 or any number of relationships. You can have a billion relationships if you want. Typically, that's a horrible idea, but your graph databases will allow that. Now, there's some guidelines as well. So guidelines you should stick to unless you know what you're doing, and then you're free to break them. This is kind of like driving in India, for example, right? Doesn't necessarily have to be the right thing to do. So get creative. please don't use the same relationship type for everything. That's usually going to lead to a horrible model that is going to be terrible for performance. Conserve your relationships. Don't use two when one will do, right? You should have relationships that know what's on the other side of that relationship, know what type of node you're going to run into, at least on one side of the relationship. If you have relationships where you don't really know what's on either side, typically that's a bad idea, and you're going to be doing a lot of filtering to figure out what you really need. Now, you're building complex paths, complex queries. You want to try to keep the relationship direction the same for often traveled paths. And if you don't, it's going to get ugly in how you write your queries. One label per node, please. This was a terrible idea to allow nodes to have more than one label. Every time people do this, it tends to be a bad idea. So just stick to one label if you can. And always index any properties you're going to use to find another node. This is a must-have if you have very large nodes that you're going to find by telephone number, social security, email address, or things beyond just their numeric identifier. Now, some people are visual, so let's just visualize some of these rules and guidelines, right? Node can have many friends, or they can have zero friends because they're a giant jerk, right? That's also a possibility. A node can have more than one relationship with another node, right? You can be friends, you can be coworkers, you can be neighbors, you can have all kinds of relationships with the person next to you. It doesn't have to be just a singular type. They each have different meanings. Now, every holiday season, you experience the joy of listening to Mariah Carey over and over and over again, singing All I Want for Christmas. And All I Want for Christmas is a new Christmas song because I'm sick of it. You can have many, many relationships of the same type between two nodes. This is going to be a problem for some databases that don't allow this kind of relationship. So be aware if that is a limitation in databases you are using. Now, relationships can also have properties, unless you're using the old antiquated triple stores. But most databases are moving toward giving you properties on relationships. They can be weights, they can be dates, they can be booleans. So see if they're active or not active. Now, why would you choose one or the other? For example, we have a person who likes a person or loves a person, or has two different types of likes relationships, one with the strength of 3 and one with the strength of 5. Well, filtering for that strength property is going to slow you down. And if this is a key part of your query performance, maybe you want to skip that and just have the different types of relationships. You know right away that a loves means strength 5, and then you can skip the having to check that property. Now, there's a lot of mistakes people make when modeling because there's no rules for modeling graph databases. There's tons of wrong ways to model your data, no right way. It's just a question of a lot of variables, including your queries, your specific database type and its capabilities, and what you're trying to do with it. So let's look at these two models. On top, you have a person that lives at an address and works at another address. On the bottom, you have a person that has two different has address relationships, one with the type of home and one with the type of work. Which is the correct way to model this? Well, when you think about it a little bit harder, most people don't have a ton of addresses. Unless you're a very rich person that owns like 20 properties or something like that, you typically have one home and you typically work at one place, unless you're one of those overemployed people that have like 3 jobs at the same time. So if you're only going to have 2, you might as well just have has address with the relationship type instead of complicating your life with the different types as you do up there. But if there's a reason why you may have a bunch of addresses, let's say you happen to be a real estate investor or something like that, and you're building a model for real estate, then you choose a different option here. Then you have the directions of 2 nodes here. We have a parent of relationship and a child of relationship. There's typically no real reason to create both. Most graph databases are going to be bidirectional, which means you can traverse the relationship from either direction, starting at either point. So if you do both, you're kind of just wasting space. Now, sometimes, though, you need those 2 relationships because they mean different things. They're asymmetric, right? So a person can follow another person on Twitter or LinkedIn or what have you, but they don't have to be followed back by that person, right? This is not Facebook where you kind of have to both be friends with each other. You can do one or the other. Sometimes, though, there is a good reason for having these one-way relationships. Now, not many graph databases have this. I think Tiger Graph is the one that comes to mind that has this kind of a by default, which is kind of strange. But imagine you're building a dating site and you swipe right for the people you like and you swipe left for the people you have no interest in. Imagine the person on the bottom right is ugly. Do they really want to know all the people who swipe left on them? Not really, right? Those are kind of just throwaway relationships. They're never going to want to know that thousands of people looked at them and said, nope. So if your database allows for one-way relationships and you really have a good use case for them, then you may want to take advantage of that. But typically, it's only reserved for a few databases. All right. Another mistake people make is sometimes thinking that relationships are relationships when they really should be nodes instead. And sometimes the way we use language influences our modeling. Did you email someone, or did you actually send an email to someone who CC'd it to someone else, who replied to that email, who forwarded it to somebody else? So careful when you are modeling how you use language and accidentally turn nodes into relationships. And then you have the problem of missing nodes. Sometimes you end up with these weird three-way relationships that are not safe for work. And it tends to mean that you're missing a core concept. And often that core concept is time. So a person had a job at a particular time from X time to Y time at a particular company doing some kind of role. And then they change positions to become a manager or director or what have you, or they change companies. Now, sometimes people have multiple jobs at the same time. That's okay. They would be modeled separately with different job nodes instead of making a complicated mess of things. So whenever you're feeling like, something is off here, think about time and think about what you're missing. That's probably what's going on. All right, moving on to queries. You can't just build your model based on data alone. You have to think about the questions you're going to ask. In front of you, you're going to see a really simple graph model that has people that acted in movies, some person that directed some of these movies, and they have the roles that they played in those movies as properties. So Tom Hanks acted in Cloud Atlas as Zachary. Hugo Weaving was Will Smoke, and he was also Agent Smith in The Matrix, and so on and so forth. And this is a perfect way to model questions about movies. But if you wanted to know who played 007, which actors played James Bond, then this is a terrible model because you're going to have a hard time trying to look for those role properties and asking to see if that role includes 007. You have to check every single role ever in your entire database. That's terrible. Instead, you would have a node for the character 007. And you would connect it to the people who played him in the movies where he appeared or cameoed or they made fun of, right? So the questions matter. Right. Data is not enough. You need to understand what you're going to be asking of that data. And I want you to remember this slide because it's going to come up again. This is what they call foreshadowing. So imagine for a second that you're going to be modeling a news feed in a graph, like Twitter, Instagram, Facebook, LinkedIn, like all of those, right? A typical newsfeed model might look like this. This might be the obvious way of doing it, where you have a user that follows a bunch of other users. These users post something on their timeline, and then they repost other things. We have a time property that tells us what time they posted something, and then whatever that status of the post was. And this looks okay, and this will work day one. But then we think about what happens when time passes, right? More posts, people keep joining the site, hopefully, and the number of posted relationships grow a lot. And you go from a few posts a day to thousands of posts a day to thousands of posts a second. Oh, no. So when you want to ask, okay, well, what did the people I follow post today? You're going to have to check through tons of these posted relationships and check that time property and see if it's today's date. And this query is going to get slower and slower as time goes on. And these users post more things or you follow more users. And that's clearly a sign that something is wrong and you need to alter your model. So one trick we can do is change the dates to be relationship types. So we can say the user posted on a particular date something. And then all I have to do now is say, all right, start from the user, find all the people I follow. Usually people don't follow more than 1,000 others, let's say on LinkedIn or what have you. And then from there, just look at today's date and maybe yesterday's date and find the posts that came out today and yesterday, sort them by datetime, and then give me those. And then that makes your query stay about the same speed regardless of what happens to your data. As your data grows, your query stays the same size, right? That's what you're looking for. Those are the magic queries that make things real nice for graph databases. That's our red door, if you will, using those dates as relationship types. Let's look at a more complicated. Yes.
But before we go into the more complicated example, there's a couple of questions that have come up. I think it goes back a little bit to verbs and tense. So Prashant is asking if it's good practice to stick to present tense verbs for relationship labels and nouns for node labels. And a follow-up to that is curious if tense of the verb in the relationship name has a bearing on the model in certain contexts.
Only you have to make a difference between something that is currently true and something that was in the past. So if you allow for relationships to be deleted but tracked, so you want to know your deleted relationships, then it makes sense to allow the tense for the past. Obviously, you can't change the relationship type, so you have to delete it and recreate it and add the posted. I tend to stick with either current or past. So I think I like the past because it says someone did something at a certain time. So I like posted and reposted. But it doesn't really matter too much as long as you keep clear track of it. You said there was a second question?
That was more my question is what happens when people confuse the relationship and node type, when they create relationships that should be nodes or inversely create nodes that should be relationships? Like what's the common problem that results from that?
Here. So sometimes you just can't model the data at all if you don't have this concept of time or this kind of in-between node that connects things together. Or you have to create lots of little tiny relationships between people. So you would have joins between the person, position, and company, and you would have like properties that would have a date and what the other node on the other end should have been. And it basically becomes a mess if you're trying to do it. There's a few databases out there that support hypergraphs, and they allow the 3 or 4 or 5 different nodes to be all in one quote unquote hyper relation. Typically, it's going to make a mess of your queries, kill your performance, and annoy the crap out of anyone trying to use this thing. So try to keep it simple if you can and stick with the 2 nodes per relationship. And if you have to invent that third hyper node, if you will, connector between the 3 or more.
Okay, thank you. Oh, and a question now that you brought up hypergraphs, you did it. A question on which databases support hypergraphs. And I would do, and do you know anybody who's actually using them? But
I want to say XG. That's the only one I can even think of. Some research ones for sure, but like none of the query languages currently support. So you'd have a one-off query language, and you're asking for over complexity already. Point of view, like I said, I could be wrong. Your mileage may vary. Okay, so I think we were here modeling something a little more complex. So this is my favorite example of modeling because it really shows you how you have to know how your database works and your query in order to model your data correctly. So how do you model flight data? This is a fun example, right? Imagine you can book a flight up to a year in advance. In a single day, an airport can have 1,000 flights. You can go to 60 different destinations and at most 40 times to one particular destination. So think about the hubs that exist at there: Charlottesville, Miami, Chicago, New York, right? Now, you want these answers to come back in less than a second, so they have to be fast. You can't waste too much time here. And the query we're going to do for our example is what flights exist from LAX to ORD. So we're going from LA to Chicago next Sunday, let's say. So the concept of mechanical sympathy is understanding how a system or a machine works and how to achieve optimal performance. First, we can try the most obvious model. Right? We have nodes for airports, and they're forming 2 different relationships. Now, if you want to actually run this query, you have with 2 index lookups to get the airport IDs. You have these 365,000 relationship traversals. It's 365 days. You'd have to check another 365,000 times, filter by date. See the 1,000 node IDs to see if we got to our actual destination. So this relatively simple query is terrible performance-wise if you model the data this way. So we could start changing things. All right, well, what if we model a flight node? What do we say? Well, an airport has a flight, and that flight has this. Well, we actually make things worse, right? Because now we have an additional 1,000 more relationships to go through. But at least, we have to try something to make this work. So let's get a little more creative about this. All right, let's think about how else could we model this data based on what we know of business case in the real world. So typically from LAX to Chicago, so we can have these airports have days. Let's say airport has a day, and on those days we have flights. So now we reduce the size of the graph we have to traverse significantly. We just have to find our starting node, find the day that we care about, do a little bit of filter on that date, and then from then on, we have a lot less relationships of flights to traverse. That helps a lot. Then we can go back to the trick I showed you earlier, using dates as relationship types, and say, all right, well, what do we do that? Well, that skips having to check those 365 airport days for a date. We can just go right to it, which is kind of cool. It's not a huge performance game, but it's nice. We can use the airport code and date as the starting point to find our airport day node, and then just traverse from there. So now we have 2 index lookups to get our node IDs, and then we have 2,000 relationships to traverse through, and 1,000 node ID checks to see if we got to destination. So our query is significantly faster by taking advantage of the fact that people fly on days, not just randomly. But then we think, well, what else can we do? We can group this together. We can say the airport day has 1,000 flights, but really they only have 60 destinations. So we can group those flights by destination and tweak our model to have even less relationships to traverse. And then we can get to a final model that kind of looks like this. We say, all right, we have an airport day, and we're going to use the relationship type of the flight destination of where they're going. So wherever airport they're going to land at from that flight becomes our relationship type. So we know right away from that airport day how many flights are going to ORD, and we don't have to look at any other flights, and we don't have to look at any other days. So now we just do one index lookup, 40 relationship traversals, and we're done, which is pretty nice, right? This is incredibly fast query compared to our starting point that had thousands and thousands of relationships that had to be traversed. This is our red door, right? Being able to use those relationship types as partitions to make a query significantly faster than if we just modeled it, quote unquote, the right way. All right. Continuing on. What about modeling relationally? Or actually, should I stop here? And any questions on this last red door?
I guess maybe summarize like how you go about figuring out the practical way based on where you're starting from, because that just seems like a lot of trial and error maybe for people to figure out.
Yes, it was a lot of trial and error. This is a use case from a real customer that took over a month to figure out. We tried the traditional way, which was really this: airport flies to another airport. Realize all the problems that we're missing by not having a flight. For example, flights have pilots and has a crew that have to be manned, and sometimes they change, and they have passengers that go on a particular flight. So it was a requirement really to have a flight node. It made sense for other reasons to have a flight node. Baggage also goes to the flight node. And then the problem began, well, we have so many relationships to traverse through to get the answer. This is where the pain started to come in. So we just have to get creative. You just have to stop thinking there's a right way to do things and start thinking, what is the simplest way I can get my answer done by looking at the least amount of the graph? It's always, the less you look at, the faster the query tends to go. So here, once again, we have these 365,000 relationships that we had to traverse as we're filtering through to get the dates that we care about. And that's when it should hit you, like, why are we checking all this date property over and over and over again? We know already one trick, which is using the relationship type, as a way to connect nodes together when I have to filter for dates. But the airport day idea was really a key change that said people don't fly from airport to airport. People fly from airport to airport on a particular day because flights have time associated with them. You don't just go. Maybe some people do, but usually you have a reason to be at a certain place at a certain time. So that idea was the changer. And then the other big change was realizing that the destinations could be grouped together and that there were only so many destinations. I think the world has something like 40,000 commercial airports. So we're not talking about like the little hobby airports where you can fly into somebody's farm, but like actual real airports, even like the little tiny ones. It's only about 40,000 of them. So they easily fit into the relationship types system or the graph database I was using at the time. I think newer graph databases can do billions of relationship types. So it was a problem before, but now it's definitely less of one. So check with your vendor. Some vendors only allow like 65,000 relationship types. But
so there's a couple questions that are probably more general that we can just open up and ask towards the end. But on this topic, there's also a question about how much of your work optimizing is through trial and error versus combing through. the internals of the graph database to actually look for solutions.
So the performance game is a fun one. First, you have to look at the profiler. And the profiler is going to tell you what the query planner thought the right way to plan the query was. That's going to be your first hint. Like, is it doing something obviously stupid? And sometimes the query optimizers don't get it right. In that case, you can sometimes tweak your query a little bit to make the optimizer, to force the optimizers to do the right thing. If you can't do that, you can always, well, not always, but typically you can use a lower level language. In Neo4j's case, we can always go to Java and rewrite the whole thing as a stored procedure to make it work and force the graph database to do exactly what I want it to do instead of having the optimizer guess as to what I want. So those are kind of like your first steps. You can just force the engine to do what you want it to do. The second part becomes, well, what if that's not enough? Right? So it's doing the right thing. The query optimizer figured out exactly what the right thing to do performance-wise to get the answer, but that wasn't enough, and now you're stuck. That's when you have to go back and say, well, can I change the model so I don't have to do all this work? And usually the optimizer or the query planner will tell you, I spent 20% of the work doing this filter or 20% of the work doing this traversal. And you look for whatever the heavy parts of the query are and you attack those and say, is there a different way? Can I get creative and go around this problem instead of through it? And that's when you get like, well, why don't we make airport codes be part of the relationship type? Like that was not something you just come up with day one. You have to head against the wall a couple of days before you figure that one out. So let's talk about modeling relationally. There's a lot of graph databases out there, including some that are relational. And you may have read the original Ted Codd paper on the relational model. And he believed in databases that had three things. One of them was nulls. So you get rid of all these null values everywhere. Their nulls are a huge mistake in databases. They make life miserable in a lot of places. Now, he believed that it would only have sets. So you wouldn't have duplicates anywhere, and everything would be a set. And he also believed that you get performance as good as the low-level application developer could write. So the query optimizers would take care of all the hard work. Now, that last one is still to be determined. Let's talk about the other two. If you will, imagine your data is a giant carrot. Okay. I know it's a bit of a stretch, but think about it that way. And what we're going to do is we're going to slice this data into tiny, tiny, tiny little pieces into something that's called graph normal form. This graph normal form is making a bunch of little tiny tables out of your regular third normal form table that are going to be made up of mostly key value or key pairs. So key value would be the property of something, a name, email, social security, whatever. And then a key would be a join table, a relationship between one node ID to another node ID. That small change. Now, let's look at a more visual example. We have a third normal form, a product table. We have, once again, our cordless power drill that has a brand, has a category, has a retailer, has a rating, has a bunch of relationships and some properties. And we're going to break it up into tiny little pieces. So we have the product just has something unique to it, like the name. And then we have brands, categories, retailer, and rating as separate tables. And then the brand, the categories, and retailers have their own table separately from that. So what's nice about this is there's no duplicates, there's no nulls. Everything is kind of clean, if you will. Now, what you do is you index both sides of the table. So one index per column. This is the part that kind of sucks because you have to do this for everything in order to make it work. But what's nice about it is that it makes it easy to find rows from either direction, right? So you wanted to know all the products that have a rating of 3.8 or all the products that came from retailer 3. Great. You can just go to the product retailer, find it by index, and get your answer. So you have all these little tables that you have to join. Lots and lots of little tables that you have to join. And typically this is a nightmare for most databases. Like they are not happy joining more than 3, 4, 5, 15, 20 tables. They're just going to blow up on you. And this is the whole reason why NoSQL even exists, the join problem. Whenever you join two tables together, you have to keep hold of these intermediate results until you join the third table, and then you have to hold the intermediate results to join the fourth table, and so on and so forth. And this will blow up your memory and make your database hardware miserable. So about a dozen or so years ago, a bunch of researchers came up with the terribly named worst case optimal joins. And what they really mean is that they can join more than two tables at a time. Now, newer databases are able to do this. So you look at DuckDB, you look at Kuzu, you look at CedarDB, and of course, relational AI, they can make use of these worst case optimal joins. And the idea is instead of joining and holding the results, we're going to hold, in some cases, the tree, in some cases, the try, in some cases, the hash, but we're going to hold kind of like where we are in the different tables along, or we're going to seek through them. And the more filters you add, the more tables you add, the more you skip, the faster the queries go, which kind of turns things on their head. Typically, the more tables you have, the slower things go. With worst case optimal joins, the more where clauses you have, the more tables you have to join, the more filters you have, the faster things go. Right? So then joining a whole bunch of little tables becomes a good time. It becomes a celebration instead of a reason to cry. All right, enough about that. Let's talk about modeling business. Right? Now, the business of graph databases is drowning in the flood of all this AI stuff. Right? Nobody cares about graph databases. It's all about different models and open source this and this and that. But they're holding on to GraphRag for dear life, right? And if you go watch a couple of the GraphRag talks, you'll listen carefully, you'll hear all these cries for help from the graph database vendors because they still want to be relevant, and luckily enough, they are. And that is the marriage of symbolic AI, if you will, with LLMs that just text, they just speak strings, they speak, they repeat what they've seen before, but they don't understand what these things mean. They don't understand the symbols that they represent. But with graphs, you can make that happen for yourself. But back to the cries for help. Matt Turk has this post on LinkedIn. And if you've been around, you'll know what he's saying is the truth, right? The problem with analytics is that the data is messy, the data is siloed, and the data is all over the place. And the problem with business intelligence and machine learning is that the data is messy, it's siloed, and it's all over the place. And now, today, the problem for AI is that the data is messy, siloed, and all over the place. So what do people do, right? They move the data around from databases to data warehouses to data lakes to data lakehouses to data meshes to data warehouse platforms. They keep moving this data around. And to be honest, it's just not enough. So some people in the back end will be like, wait, I know they need a semantic web to make this all work. And it's like, no, listen, they've been trying for 20 years to make the semantic web a thing, and it hasn't gone anywhere. It's gone absolutely nowhere. Just drop it. We don't need a semantic web. That's not the answer. The answer is it's not that, because data is not enough, right? Data is not enough. You need lore. Now, the trickies in the room will remember data's twin brother, typically evil, usually conniving, very smart, but lore is your business. It's what separates your business from the competition. Lore means the traditions and knowledge of the subject of, that have been passed down between one executive to the next about how the business actually works and how it runs, and what separates from you from your competitors. So, for example, you have two business rules. These are rules that are not in the data that says, I'm going to consider a client to be high risk if their yearly income is lower than the average income of my other clients. One bank may say that. And the other bank may say, no, hold on. I consider a client to be high risk if their debt is larger than double their yearly income. And that's when I worry. So there are two different ways to look at risk that are incompatible with each other. But neither one is in the data. It's just how each business decides to define what they consider to be a high-risk client. So you have this knowledge graph, and they're both adding business rules to this knowledge graph that are separate, and it's not in the data. The rules typically exist in thousands of lines of Java, Python, and C++ code in many different places all over their systems, but they're not in the data itself. Right? It always reminds me of this line from Mad Men, right? You have Lucky Strike, it's toasted. Everyone else tobacco is poisonous. No, it's the same 7 companies selling tobacco, selling the same products, but it's how they treat the business, how they think about their business that sets them apart from each other. Once again, you may have a few folks in the back going, wait a minute, we did this already. We invented this thing called Swirl. It was semantic web rule language like 20 years ago to handle this logic stuff. It's like, listen, yeah, there was something there that they tried to do. It wasn't very powerful. It didn't do anything beyond first order logic, and it went nowhere like most of the semantic web. And you know what? We're not here to talk about the past. We're here to learn about the future, about real knowledge graphs, not just data. So what is a real knowledge graph to me? It's a knowledge graph that handles 3 different concepts very well. One is obviously the data itself. You have to have this. These are your knowledge relationships, properties, and types. So you have a name, a date of birth, you have an address, you have a picture as a bitmap that can also be part of the data. And you have these relationships where the person is named John, or they were born in a particular date, they live in a particular city, and they look like this picture of a bitmap that we saw earlier. And most vendors can handle data at level 1, some better than others, but most of them can handle that. Then you get to level 2, which are queries. And the way I like to think about it is by thinking about views. Does your database support views? And you'll find that some of them don't. Yeah, you can kind of fake it with streaming queries or how to kind of just having stored procedures that save the queries somewhere in the system, make a bit of a big mess, but they don't really understand views. So by views, I mean things like, well, what's a person's age? Well, it's today's date minus the date of birth. So it changes all the time. It changes whenever we query the data for that answer. A person has one date of birth. That's a rule, a constraint, or invariant we can add to our system. You can say, well, a person has a grandmother if it has a has-mother relationship in a row, or has-father, has-mother, 2 hops away. Either one will work for having a grandmother. And knowledge can be used, can be inferred from existing knowledge without having to materialize this. Materializing means creating another relationship for this. So instead of having every single person in your graph have a has-grandmother relationship to their 4 grandmothers, you just have that as a view. And whenever you query for them, you'll insert that part of the traversal into your system and go from there. So if your database doesn't have that, it's not really able to handle the queries part of a knowledge graph. And then we get to the third level. This one is harder. That's intelligence. That's reasoning. Can your database system think about the problem? We don't know what your age is. Well, okay, but we know the age of all your friends. And it's likely that your age is the average age of all your friends. Is it going to be 100% correct? No, but it's a pretty reasonable assumption. We can say things like, well, what's the fastest way to ship a big container from place X to place Y? Well, you might need a solver to help you answer those kind of questions. What kind of product will this person buy next week? Now you're looking at neural probabilistic reasoning. So these concepts of graph reasoning, rule-based reasoning, prescriptive reasoning, predictive reasoning, these are things that if your database can't handle, then they're not really using that knowledge beyond having data. It's not able to just reason, it's not able to think. And if your database has all 3, then congratulations, because you probably are using relational AI. And that's all I have for my talk. I'll start and ask or answer any questions.
Let's start with a question that came in earlier from Thomas. And that was on modeling hierarchy and the fact that that can sometimes be very useful. Is there a blessed way, or maybe it's a good way, to do this without using multiple labels? I am going to open up Thomas's mic. And Thomas, if you'd like to kind of iterate that question with a little more detail.
All right. I think I'm coming through. Okay. So there was, let's say, one client and they had employees. And not only were there employees, but there were also managers. Not only were there managers, but there were directors, et cetera, et cetera. And they had certain queries that were for everybody, relevant to all employees, and queries that were only relevant to directors. And so, this ended up with some nodes having, let's say, 5 labels of all of the different, not only are they a director, but they're also a manager and they're also an employee. And
if you're a manager, you have a title of manager somewhere. Or you can say a manager is someone who has a manager's relationship to one or more people. And if they're a director, typically they have a director title you can set as a property level. Or typically employees have level IDs, right? Most companies now have if you're level 12, you're probably a manager. If you're level 13, you're a senior manager, 14, associate director, 15, director, and so on and so forth. So you can manage that with just properties or nodes.
Fair enough. And so, so I guess that trade-off leans more towards properties than labels itself.
Yeah, all a label is a property. It's just an easier way to define the most important part of a node. It's a person. So I would try to distill it down to the basics, like what is this thing? Is it a person or is it a piece of equipment? What is it? And then kind of go from there. And everything else can just be a property.
Thank you.
I will ask the question that I had next, which is that some of what you're suggesting is so use case specific. And I'm just wondering, when you change use cases at a company, if you end up having to remodel your data itself.
Yeah. So this is the issue with trying to build a all-encompassing graph database for everything, right? So when you're trying to build a knowledge graph, about your business, it might make sense to model it in a simpler way that's not optimized to any one particular query or another. You're just going to use it for like memory for your AI system. Great. Then keep it simple. But we do specialized modeling for specific queries that have to be real time or as close to real time or where performance really matters. These are what we call the money queries, right? The reason for you wanting to move things into a graph database to get the speed up that you can't get anywhere else. So that's when it might make sense. Now, nothing says you can't model multiple graphs in one graph system. You can have different layers of modeling for a graph system as well. There's no rule that says you can duplicate your data or make a copy of your data in a separate format. Relational databases have been doing this for years when they denormalize things in order to avoid joins just to make performance work. It's the same exact idea with graphs. You don't have to, only have one copy of the data.
Got it. And with that, then you end up having multiple graphs at a company for the different departments and the different uses, or even, the same department, but multiple use cases within a department.
Typically, departments that are building applications care about the money query for their application. When you're trying to build an enterprise knowledge graph, then things get more interesting. Now you want one graph that encompasses the entire business. So you can ask questions from shipping and receiving all the way to your last piece of revenue in accounting or billing or whatever. So I think they're two very distinct ideas. Enterprise knowledge versus a use case query type graph where performance matter more than cohesiveness. And for those who are embarking on building enterprise knowledge graphs, don't try to boil the ocean and build the entire thing. It's going to take forever and you'll never get there, especially if you have the semantic world on the team arguing over what the word person means. Instead, just start with one department, model it the best they can, and then go to the next department and tie it on or attach it to the graph and kind of just tackle it one at a time. If you try to do it all at once, you're just never going to get anywhere.
What is some of the pushback you get, on some of these concepts and some of your tips and guidelines here?
People who love third normal form or are RDF style folks, they hate this idea that you can just model any way you want and go crazy with the relationship types. It feels unnatural to them, almost a bastardization of the data. You can do this. But once again, we've been doing this with relational databases forever in the name of performance. So why would you not do it in graph databases for the same exact reason? And if you reach the limits of your query optimizer and you reach the limits of what your programmatic API can do, then you have to get creative with your data model. Otherwise, you're stuck.
And I think maybe a little on this topic, Louis Vuitton states that, to be fair, though, the semantic side has brought an interesting way to encode business rules. So from a business rule standpoint, especially when you're using some of the other tools, looks like Louis is just recommending we take a look at that as well.
Yeah, I mean, the problem with the semantic stuff is they got stuck. For a lot of those rules, you can't go beyond first normal form, or first order, and you kind of get stuck there. And the complexity of the rules of businesses are encoded in programming languages, right? They're in your Python and your C++ and your Java code. And it's very hard to translate that into a generic semantic form that makes any kind of sense with any kind of performance at all. So I think business rules have to be encoded in something more powerful than that. We just published, Relational AI just published a paper today on RHEL, its internal language that it uses for rules, but they can be done in other systems using programming like languages that are able to handle complex logic beyond what semantic web languages have done in the past.
I believe we're going to see a lot more about rules and logic and how to integrate them into our knowledge graphs kind of going forward. It's definitely going to be an important topic. To pick up on the thread about relational AI, Veronique actually has a question about the difference between relational AI and neurosymbolic AI. If so, how would you describe that difference?
Okay, first we have to back up and say one's the name of a company and the other is the whole topic of science. The difference or the kind of the marriage of the two systems are with LLMs, the strings not things or things not strings quote that I've heard before, right? Where you can't treat the data as just strings. You have to understand what it means. Otherwise you get errors like how many R's in strawberry, and you end up with 2 instead of 3, because they don't understand what the letter R means. To them, it's just text. So they see a lot of people put 2 in their answers, and therefore the answer becomes 2 when it's incorrect. So with graphs, you're extracting from the text things, right? These nodes, these relationships, there are things in there, how things are connected to each other. And when you marry the two, you get better results than if you only use one or the other. That's typically, the truth of any system. The more intelligence you can add to it, the better things go. The thing that relational AI brings is this concept of reasoning on top of your data, and then these views on top of views on top of views on top of your data. And I would just start and ask and say, does my current graph system support views? And if it doesn't, why? And the trick there is materialization, right? If your system has to materialize every single relationship in order to be performant, or in order to be able to even answer the query, you're going to run into problems because your data is going to blow up. You'll need massive amounts of storage and memory in order to handle the graphs if you have to materialize every little thing. So just be aware of that problem.
So as we start to wrap things up here, you've been doing this a long time and have seen a lot of different real world scenarios and probably messes. If there's one thing to keep in mind for the people that have to model graph data, what would that be?
You have to get to know your system, get to know how it really works underneath the covers. I showed an example of mechanical sympathy earlier. That was the F1 car. If you want to become an expert in your graph data system, you have to know what it is doing every single time, right? When you're going back to the example of modeling flights, for example, what actions is the database doing? Is it doing an index lookup? Is it doing a relationship traversal? Is it checking a label or a property? And how much does that cost? Some systems, for example, when you check a relationship property, they slow down by 2. Some systems slow down by 50, right? So if your system slows down significantly by having to check a relationship property, then you absolutely do not want to have relationship properties in your money queries, if you will. You want to stay away from that. Some systems have labels for free, where your labels are stored separately from your properties, and they're very fast to gather them and group them. They're stored in bitmaps or what have you. And you can join labels together using bitmaps, which is very fast. So get to know the inner workings of your system. Usually the vendor will have documentation or video somewhere that you can reason about, so that when you run into performance problems, you can not get stuck just looking at the query optimizer and go beyond that and say, what else can I do?
So we're getting appreciation for a great talk. One question about, or whether you have a link to that paper you mentioned that just dropped today. If you have it up, great, stuff it in the chat, and I will put it in the links as well. Max is fairly active in the GraphGeeks Discord. You can reach out to him there, but also find him on LinkedIn. So again, thanks, Max. It's always very helpful, always good practical advice. There we go.
Thank you very much. Here's the link.
All right. Thank you, everybody.